In class and for homework, we've done a lot of chain rule examples. What I want to do in this video is return to an example that I did in class, or an example similar to it, I forget exactly, that maybe now that you've done a bunch of the mechanics and using the inner function, outer function rules, maybe will help make that rule make a little bit more sense. So let's give it a shot. So here's a problem I want to think about. So we have some circle that's expanding. And at time t equals 3, the radius is 5 centimeters, say. And at that particular time, t equals 3, the radius is increasing at a rate of 2 centimeters per second. And we want to know how fast is the area of the circle increasing at time t equals 3. So let's start by just reminding ourselves the formula for area of a circle. A is a function of r. Well, that's pi r squared. Area is pi r squared. So we can find the derivative of that, a prime of r, and that's just 2 pi r. So that says how much extra area you get if the radius at r increases by 1, how fast it changes with respect to r. So we need to use the chain rule because we're interested in how area is changing over time. So this is how area is changing with respect to radius, but we want to know how area is changing over time. And well, this is a change situation because area is changing with radius, and radius is changing with time. So area changes because the radius changes, and then the radius changes with time, and multiplying these together gives us dA dt, the rate of change of the area with time. All right, so now we pretty much have all the ingredients. We can just use this formula. So we've got dA dr, and let's see. So this is going to be at t equals 3, just a reminder. So dA dr, that's 2 pi r, and at t equals 3, r is 5. So I guess maybe I can write this out like this, 2 pi r dr dt. So here I just said dA dr, that's 2 pi r. Now let's plug in t equals 3. So at t equals 3, r is 5. So this is 2 pi times 5, and then dr dt, well, that's this, 2 centimeters per second. That's how fast r is increasing. So that's going to be, let's see, times 2. And 5 times 2 is 10, and 10 times 2 is 20. So this whole thing is 20 pi. Okay. So what I want to do now is solve the same problem a slightly different way. So I guess I'll start a fresh piece of paper, but it's going to be describing the same situation. So now I'm going to view this function like this. So I've got a, that's a function of r, that's a function of t. Of course, this is just what we were thinking before, but now we're just writing it a different way. We're making it maybe a little clearer that this is a composite function. You start with t, and you r it, and then you a it. Okay, so then we might want to know, well, what's d dt of a of r of t? In other words, how fast is area changing with time? So this is a chain rule situation. We take the derivative of the outer function, leaving the inner function alone. So this is the derivative of the outer function, leaving the inner function alone. Then I need to multiply that by the derivative of the inner function. The inner function here is r of t. I don't have a formula for that, so I just call that r prime of t. All right. So a prime of r, we figured that out before. It's 2 pi r. So a prime of r is 2 pi r. And then, I guess I'll write this r of t r prime of t. So then we need to know what's going on at t equals 3. So then dA dt is 2 pi times r of 3 times r prime at 3. So I just plug in time 3 to figure out the rate of change at t equals 3. We're told in the problem that when t equals 3, r is 5. And we're also told, in the problem, that when t equals 3, r prime is 2. So again, we get 20 pi. So this isn't anything new, and you've done a lot of examples like this, but I thought it might be useful to connect this sort of word problem about which perhaps you have some intuition, or there's some physics or geometry you can connect to this notation that I think for some people still seems a little bit abstract. I mean, understandably so, because it is a little bit abstract. Anyway, hopefully this example will help some.